Volcanoes are among the most awe-inspiring natural phenomena on Earth, embodying both creative and destructive forces. They are formed by the movement of tectonic plates and the escape of magma from beneath the Earth's crust. Volcanoes form when molten rock, known as magma, from the Earth's mantle, rises through the crust and reaches the surface. This process is intricately linked to the movement of tectonic plates. The Earth's lithosphere, divided into several large and small plates, is constantly moving due to convection currents in the underlying asthenosphere. These movements can create conditions conducive to volcanic activity in several key settings. Divergent plate boundaries. At divergent boundaries, tectonic plates move apart, creating space for magma to rise from the mantle and fill the gap. This process forms mid-ocean ridges and rift valleys, where shield volcanoes and fissure eruptions are common. Convergent plate boundaries. When two plates collide, one is often forced beneath the other in a process known as subduction. The descending plate melts as it sinks into the mantle, generating magma that can lead to the formation of stratovolcanoes in subduction zones. Hotspots. Some volcanoes form far from plate boundaries, over hotspots where plumes of hot mantle material rise toward the surface. As the tectonic plate moves over the stationary hotspot, a chain of volcanoes can form, such as the Hawaiian Islands. The composition of magma plays a crucial role in determining the type of volcano that forms and the nature of its eruptions. Magma varies in its silica content, which affects its viscosity or resistance to flow. Basaltic magma. Low in silica and highly fluid, basaltic magma produces gentle eruptions that create broad shield volcanoes. The low viscosity allows magma to flow easily, spreading out over large areas before cooling. Andesitic magma. With intermediate silica content, andesitic magma is more viscous and can trap gases, leading to more explosive eruptions. This type of magma is typically associated with stratovolcanoes. Rhyolitic magma. High in silica, rhyolitic magma is extremely viscous and prone to trapping gases. This can result in highly explosive eruptions, often forming volcanic domes or calderas. The physical structure of a volcano depends on the characteristics of the eruptions that built it. Volcanoes can be simple, like cinder cones, or highly complex, like stratovolcanoes or volcanic fields. Cinder cones, small, steep-sided cones formed by explosive eruptions that hurl pyroclastic material into the air. These volcanoes usually have a single vent and a short-lived eruptive history. Stratovolcanoes, large, conical volcanoes built from alternating layers of lava flows, ash, and other volcanic debris. These volcanoes are often associated with violent eruptions and are found in subduction zones. Shield volcanoes, broad, gently sloping volcanoes formed by the accumulation of low-viscosity lava flows. Shield volcanoes are typically associated with hotspots and divergent boundaries. Volcanic eruptions are driven by the release of gases dissolved in magma. As magma rises toward the surface, the decrease in pressure allows these gases to expand and escape, propelling magma out of the volcano. The composition and amount of volcanic gases, such as water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide, can greatly influence the eruption's intensity and environmental impact. Pyroclastic materials. These are the fragmented pieces of rock and volcanic debris ejected during explosive eruptions. They include volcanic ash, lapilli, volcanic bombs, and pumice. Pyroclastic flows, which are fast-moving currents of hot gas and volcanic matter, are particularly deadly and can travel at high speeds down the slopes of a volcano. Volcanic eruptions pose significant risks to human life and the environment. This section will discuss the various hazards associated with different types of volcanoes. Lava flows. While typically slow-moving, lava flows can destroy anything in their path. The type of lava flow depends on the viscosity of the magma, with basaltic flows spreading out widely and rhyolitic flows creating steep, thick deposits. Ashfall. Volcanic ash can spread over vast areas, causing respiratory problems, damaging infrastructure, and disrupting air travel. Lahars. Volcanic mudflows, or lahars, are formed when volcanic material mixes with water, often from melting snow or ice. Lahars can be highly destructive, sweeping away buildings and infrastructure. Volcanic gases. The release of gases like sulfur dioxide can lead to acid rain and contribute to climate change by cooling the atmosphere. Understanding these fundamentals is essential for studying and predicting volcanic activity, as well as for developing effective mitigation strategies. Shield volcanoes and fissure eruptions represent the less explosive, but still highly significant, side of volcanic activity. Shield volcanoes are among the largest and most massive volcanic structures on Earth. Their broad, gently sloping profiles are the result of countless eruptions of low-viscosity basaltic lava that can travel great distances before solidifying. These eruptions are generally non-explosive, allowing the lava to flow freely across the landscape. Formation process. Shield volcanoes typically form over hotspots or at divergent plate boundaries. The continuous flow of basaltic lava builds up layer upon layer over time, creating the characteristic shield-like shape. The eruptions are often long-lasting, with lava fountains or flows that can persist for months or even years. Notable examples: Mauna Loa and Kilauea in Hawaii are the most famous shield volcanoes, with Mauna Loa being the largest volcano on Earth by volume. These volcanoes are part of the Hawaiian Emperor Seamount chain, which formed as the Pacific Plate moved over a stationary hotspot. Fissure eruptions occur when magma escapes through long cracks or fissures in the Earth's crust, rather than through a central vent. These eruptions can produce vast quantities of lava, covering extensive areas with basaltic lava flows. Fissure eruptions are particularly common at mid-ocean ridges and rift zones, where tectonic plates are pulling apart. Formation process. Fissure eruptions are typically associated with divergent plate boundaries, such as the Mid-Atlantic Ridge. As tectonic plates move apart, magma rises to fill the gap, creating a linear fissure from which lava can pour out. These eruptions can produce large lava fields, known as flood basalts, that can cover thousands of square kilometers. Notable examples: the Laki fissure in Iceland is one of the most famous fissure eruptions in history. The eruption, which began in 1783, released an enormous amount of lava and gas, leading to a catastrophic impact on the environment and population. The Deccan Traps in India, formed by a series of fissure eruptions around 66 million years ago, are another notable example, covering an area of over 500,000 square kilometers. Basaltic lava is characterized by its low silica content, which gives it a low viscosity and allows it to flow easily across the landscape. This fluidity is responsible for the broad, gentle slopes of shield volcanoes and the extensive lava fields created by fissure eruptions. Pahoehoe and R lava. Basaltic lava can take on different forms depending on its flow characteristics. Pahoehoe lava is smooth and ropey, forming when the lava is still relatively fluid. In contrast, R lava is rough and jagged, resulting from cooler, more viscous lava that breaks apart as it flows. Lava tubes. In shield volcanoes and fissure eruptions, lava can flow through channels known as lava tubes. These tubes insulate the lava, allowing it to travel long distances without cooling and solidifying. Lava tubes can eventually drain, leaving behind long, tunnel-like structures. While shield volcanoes and fissure eruptions are generally less explosive than other types of volcanic activity, they can still have a significant impact on the environment. The large volumes of lava produced can reshape entire landscapes, burying ecosystems and altering river courses. Volcanic gases. Even though these eruptions are less explosive, they can release large amounts of volcanic gases, including sulfur dioxide, carbon dioxide, and water vapor. The release of sulfur dioxide can lead to the formation of volcanic smog, VOG, which can have harmful effects on respiratory health and vegetation. Long-term effects. The cooling and solidification of extensive lava flows can create new landforms, such as plateaus and plains. Over time, these areas can become colonized by plants and animals, leading to the development of new ecosystems. The 2018 eruption of Kilauea, one of the most active volcanoes on Earth, serves as a prime example of the dynamics and impact of shield volcanoes and fissure eruptions. Over several months, Kilauea produced extensive lava flows that destroyed homes, reshaped the coastline, and created new land. Eruption dynamics. The eruption began with increased seismic activity and the opening of new fissures on the volcano's lower east rift zone. Lava fountains and flows emerged from these fissures, covering residential areas and flowing into the ocean. Environmental and human impact. The eruption resulted in the destruction of over 700 homes and the displacement of thousands of residents. The lava flows created new land at the ocean's edge, while the emission of volcanic gases and ash affected air quality and visibility. Volcanic monitoring and mitigation. The eruption highlighted the importance of volcanic monitoring and early warning systems. Scientists were able to track the movement of magma and provide timely information to the public, helping to minimize the loss of life. Stratovolcanoes, also known as composite volcanoes, are some of the most iconic and dangerous volcanic structures on Earth. They are characterized by their steep, conical shapes and their tendency to produce highly explosive eruptions. Stratovolcanoes are formed by the accumulation of alternating layers of lava flows, volcanic ash, and other pyroclastic materials. These layers build up over time, creating the steep-sided, conical shape that is characteristic of stratovolcanoes. Multiple eruption phases. Stratovolcanoes typically undergo multiple phases of eruption, with each phase contributing to the buildup of the volcanic structure. The eruptions can vary in intensity, ranging from effusive lava flows to explosive pyroclastic eruptions. Crater and caldera formation. The summit of a stratovolcano often contains a crater formed by explosive eruptions. In some cases, a large caldera can form when the summit collapses into the emptied magma chamber following a massive eruption. Stratovolcanoes are often associated with andesitic magma, which has a higher silica content than basaltic magma. This makes the magma more viscous and capable of trapping gases, leading to explosive eruptions. Eruption styles. The high viscosity of andesitic magma results in a range of eruption styles, from effusive lava flows to explosive pyroclastic eruptions. The trapped gases can cause the magma to fragment violently, producing ash columns, pyroclastic flows, and volcanic bombs. Volcanic Explosivity Index, VEI. The intensity of stratovolcano eruptions is often measured using the Volcanic Explosivity Index, VEI, which ranges from O, non-explosive, to 8, megacolossal. Many stratovolcanoes have produced eruptions in the VEI 4 to 6 range, making them highly dangerous. Pyroclastic flows are fast-moving currents of hot gas, ash, and volcanic debris that flow down the slopes of a volcano during explosive eruptions. They are one of the most dangerous aspects of stratovolcanoes, capable of destroying everything in their path. Formation and behavior. Pyroclastic flows form when an eruption column collapses or when a lava dome or lava flow breaks apart. These flows can travel at speeds of up to 700 km per hour, 435 miles per hour, and reach temperatures of up to 1000 degrees Celsius, 1830 degrees Fahrenheit. Impact on human life. The high speed and extreme temperatures of pyroclastic flows make them deadly. Historical eruptions, such as the 1902 eruption of Mount Pelée, which destroyed the town of Saint-Pierre in Martinique, demonstrate the catastrophic potential of these flows. Some of the most well-known and studied volcanoes in the world are stratovolcanoes. Their eruptions have shaped human history and geography, leaving lasting legacies. Mount Vesuvius. The eruption of Mount Vesuvius in AD 79 buried the Roman cities of Pompeii and Herculaneum under meters of ash and pumice, preserving them for centuries. This eruption is one of the most famous in history and serves as a stark reminder of the power of stratovolcanoes. Mount St. Helens. The 1980 eruption of Mount St. Helens in the United States was one of the most significant volcanic events of the 20th century. The eruption produced a massive lateral blast, pyroclastic flows, and lahars, resulting in widespread devastation and the loss of 57 lives. Mount Fuji. Japan's iconic Mount Fuji is a stratovolcano with a history of explosive eruptions. The most recent eruption in 1707, known as the Hoei eruption, deposited ash over a wide area, including the city of Edo, modern-day Tokyo. The 1815 eruption of Mount Tambora in Indonesia is one of the most powerful volcanic eruptions in recorded history. It had far-reaching effects on global climate and human societies, making it a critical case study for understanding the impact of stratovolcanoes. Eruption dynamics. Mount Tambora's eruption was a VEI 7 event, releasing an enormous amount of ash and sulfur dioxide into the atmosphere. The eruption column reached a height of 43 kilometers, 27 miles, and pyroclastic flows devastated the surrounding region. The year without a summer. The eruption of Mount Tambora led to the year without a summer in 1816, as the volcanic ash and gases in the atmosphere caused global temperatures to drop. This led to widespread crop failures and food shortages in Europe and North America. Human and environmental impact. The eruption caused the deaths of an estimated 71,000 people, primarily due to starvation and disease following the destruction of crops and infrastructure. The global climatic effects of the eruption also contributed to social unrest and migration. Calderas and supervolcanoes represent the most extreme forms of volcanic activity, with the potential to cause global-scale devastation. A caldera is a large, basin-shaped depression that forms when a volcano's summit collapses into the emptied magma chamber following a massive eruption. Caldera-forming eruptions are among the most explosive and destructive volcanic events. Eruption and collapse. The formation of a caldera begins with a large, explosive eruption that empties the magma chamber beneath the volcano. The overlying rock then collapses into the void, creating a depression that can be several kilometers wide and deep. Post-caldera activity. After the formation of a caldera, volcanic activity may continue within the depression. This can include the eruption of lava domes, the formation of new cones, and the emission of volcanic gases. Supervolcanoes are capable of producing eruptions with a VEI of 8, the highest level on the scale. These eruptions release immense amounts of magma, ash, and gases, with the potential to cause long-term changes to the global climate and environment. Characteristics of supervolcanoes. Supervolcanoes are often associated with large calderas and extensive volcanic fields. They do not erupt frequently, but when they do, the effects are catastrophic. Examples of supervolcanoes: the Yellowstone caldera in the United States, the Toba caldera in Indonesia, and the Taupo caldera in New Zealand are some of the most well-known supervolcanoes. These volcanoes have produced some of the largest eruptions in Earth's history. Supervolcano eruptions have the potential to cause significant and long-lasting effects on the global environment and climate. The release of large volumes of volcanic ash and gases into the atmosphere can lead to dramatic changes in weather patterns and global temperatures. Volcanic winter. The injection of sulfur dioxide into the stratosphere can lead to the formation of sulfuric acid aerosols, which reflect sunlight and cool the Earth's surface. This can result in a volcanic winter, with severe impacts on agriculture and food supply. Mass extinctions. Some supervolcano eruptions are believed to have contributed to mass extinction events in Earth's history. For example, the eruption of the Toba supervolcano around 74,000 years ago is thought to have caused a severe bottleneck in human populations. Given the potential impact of supervolcano eruptions, monitoring and understanding these colossal structures are critical. Scientists use a variety of techniques to study supervolcanoes and assess the likelihood of future eruptions. Seismic monitoring. Earth quakes and ground deformation are often precursors to volcanic activity. Seismic monitoring networks around supervolcanoes can detect signs of magma movement and provide early warnings of potential eruptions. Geothermal and gas emissions. Monitoring the emission of volcanic gases, such as carbon dioxide and sulfur dioxide, can provide insights into the state of a supervolcano's magma chamber. Changes in gas emissions can indicate increasing volcanic activity. Public awareness and preparedness. Educating the public about the risks associated with supervolcanoes and developing emergency response plans are essential for mitigating the impact of future eruptions. The Yellowstone caldera, located in Yellowstone National Park in the United States, is one of the most studied and closely monitored supervolcanoes in the world. Its potential for future eruptions has made it a focus of scientific research and public interest. Geological history. The Yellowstone caldera has experienced 3 major eruptions in the past 2.1 million years, with the most recent occurring around 640,000 years ago. These eruptions have shaped the landscape of the park and left behind a complex system of geothermal features. Current activity. While there are no signs of an imminent eruption, Yellowstone remains an active volcanic system. The park is home to numerous geysers, hot springs, and fumaroles, which are fueled by the underlying magma chamber. Monitoring and research. Scientists at the Yellowstone Volcano Observatory, YVO, continuously monitor the caldera for signs of volcanic activity. Research efforts are focused on understanding the behavior of the magma chamber and assessing the potential impact of future eruptions. Volcanoes are natural wonders that pose significant hazards to human life, property, and the environment. Lava flows are rivers of molten rock that move slowly down the slopes of a volcano during an eruption. While they are generally less deadly than other volcanic hazards, lava flows can cause significant damage to property and infrastructure. Types of lava flows. Lava flows can vary in viscosity and speed depending on the composition of the magma. Pahoi lava is smooth and fast-flowing, while R lava is rough and slow-moving. Both types of lava can cause extensive damage to buildings, roads, and agricultural land. Mitigation strategies. Mitigating the impact of lava flows involves land use planning, hazard mapping, and the construction of diversion barriers. In some cases, lava flows can be slowed or redirected using explosives or water cooling. Evacuation and warning systems. The best way to mitigate the risk of pyroclastic flows is through early warning systems and timely evacuations. Monitoring seismic activity and eruption columns can provide crucial information about the likelihood of pyroclastic flows. Case study: Mount Unzen. The 1991 eruption of Mount Unzen in Japan produced a series of pyroclastic flows that killed 43 people, including several volcanologists. The eruption highlighted the importance of accurate hazard assessment and the need for improved evacuation planning. Lahars are destructive volcanic mudflows that occur when volcanic debris mixes with water, typically from melting ice, snow, or heavy rainfall. Lahars can travel at high speeds down river valleys, burying communities and causing widespread destruction. Formation and behavior. Lahars can be triggered by volcanic eruptions, heavy rainfall, or the sudden release of water from a volcanic crater lake. They can travel long distances and accumulate large amounts of debris, increasing the destructive power. Hazard mapping and early warning. Hazard mapping and the installation of lahar detection systems are critical for reducing the risk to communities living near volcanoes. Early warning systems can provide residents with the time needed to evacuate to higher ground. Case study: Nevado del Ruiz. The 1985 eruption of Nevado del Ruiz in Colombia produced a deadly lahar that buried the town of Armero, killing over 23,000 people. The disaster underscored the need for better hazard communication and preparedness. Volcanic ashfall is a common hazard associated with explosive eruptions. Ash can travel hundreds of kilometers from the eruption site, affecting communities, agriculture, and air travel. Health and environmental impact. Volcanic ash can cause respiratory problems, contaminate water supplies, and damage crops. The fine particles of ash can also pose a significant risk to aircraft, leading to engine failure and other hazards. Ashfall preparedness. Communities at risk of ashfall should have preparedness plans in place, including stockpiling food and water, using masks to protect against inhalation, and staying indoors during heavy ashfall events. Case study: Eyjafjallajökull. The 2010 eruption of Eyjafjallajökull in Iceland produced a massive ash cloud that disrupted air travel across Europe for several weeks. The eruption highlighted the need for improved ash cloud monitoring and communication between aviation authorities. Volcanic gases, such as sulfur dioxide, carbon dioxide, and hydrogen sulfide, are released during eruptions and can pose serious health risks to humans and animals. In some cases, volcanic gas emissions can lead to long-term environmental damage. Health effects. Exposure to volcanic gases can cause respiratory problems, skin irritation, and eye damage. In high concentrations, some gases, such as carbon dioxide, can be lethal, as they can displace oxygen and cause asphyxiation. Monitoring and mitigation. Monitoring volcanic gas emissions is essential for assessing the risk to nearby communities. Mitigation measures may include evacuation, the use of gas masks, and the installation of gas detection systems. Case study: Lake Nyos. In 1986, a sudden release of carbon dioxide from Lake Nyos, a crater lake in Cameroon, caused the deaths of nearly 1,800 people and thousands of animals. The disaster led to increased efforts to monitor and mitigate the risk of volcanic gas emissions from crater lakes. Effective volcanic risk management requires a multidisciplinary approach that combines scientific research, monitoring, hazard mapping, public education, and emergency planning. Volcanic observatories. Volcanic observatories around the world play a crucial role in monitoring active volcanoes, conducting research, and providing early warnings to communities at risk. Community engagement. Engaging with local communities is essential for building resilience to volcanic hazards. Public education campaigns, drills, and the development of community-based emergency response plans can help reduce the impact of volcanic disasters. International cooperation. Volcanic hazards often transcend national borders, making international cooperation vital for sharing knowledge, resources, and best practices in volcanic risk management. Volcanoes are among the most awe-inspiring and dangerous natural features on Earth. Understanding their behavior, the hazards they pose, and the ways in which we can mitigate these risks is essential for safeguarding human life and property. From the explosive eruptions of stratovolcanoes to the colossal impact of supervolcanoes, the study of volcanoes offers valuable insights into the dynamic forces that shape our planet. Through continued research, monitoring, and community engagement, we can better prepare for and respond to volcanic events, ensuring that the benefits of living in a volcanically active world are balanced with the necessary precautions to protect lives and livelihoods.